Anyway, so we're going to understand how basically we have the Ethernet header, we have the IP header, and we saw that each of those headers have addresses. In Ethernet, we have MAC addresses. In IP, we have IP addresses. So we're going to understand how those are linked together. Okay, and knowing the IP address, how can I know the MAC address? It's really important because we cannot use MAC address of any random one. There should be here a rule. Then we're going to understand what are, first of all, the parameters that I need to configure. So, of course, we need to have an IP address to be able to send packets. Just as when we need to make a call, we need to have a phone number. That's the way it is. Even though I'm just making a call, I need to have a phone number on my own. So the same goes with IP. But what we'll see that actually is not just about the IP address. We have multiple other parameters that need to be set up and so discovered. So how do I learn about those parameters? So this is pretty important. Then we will see that regarding the MAC addresses that we discussed before, we have a protocol which is ARP. And this is what basically will let us learn about the MAC addresses that we need to fill in the frame that will encapsulate our IP packet. And we will finish with NAT because NAT is something that we use every day. Which allow us actually to use private IP addresses because we don't have enough public IP addresses. So let's start. So I'm sorry about this. I don't know why the thing. So, okay, so we have our IP packet here is represented in blue, all right? So the blue box here is the IP packet, all right? And the IP packet needs to be encapsulated in a frame. So which means that we are adding a header, all right? And so the header that we are adding comes with a MAC address. And we have multiple types of MAC addresses. And the main two types of MAC addresses that I have the broadcast, which is the old F, and there's an F missing here. I don't know the reason, but there's an F missing. So you may remember that the MAC address is basically 6 bytes. And 1 byte is translated in hex, in the hex value. And we put dots, right? A, B, so those are 2 hex numbers, dots, 2 other hex numbers, and so on. And we need 6 bytes this way. So we need 12 hex numbers. And so the thing here, we have a specific one, which is the all one MAC address. So if I put all ones everywhere here, I'm going to end up having FFF, FFF, FFF. And what it means that actually if I send a packet encapsulated in a frame, and the destination address of this frame is the broadcast Ethernet address, all ones, which translate to FFF, it means that anybody will see the frame, but that's already the case because when I'm on a network, usually we are all connected to the same medium, to the same channel, like here when we're talking together, right? I speak once, everybody can hear me. But here what we mean by using the broadcast, it means that the packet will be passed by any device to the layer 3. So it means that I cannot filter the frame based on the MAC address because I'm using the broadcast, and the frame should be basically passed to the layer 3 to everybody else. Another type of MAC address that I have is a unicast MAC address, which means that that MAC address is identifying a unique interface on the network. So it means that if I need to send the frame or the packet to only one, it means that everybody going to receive the frame, but some of you, those who don't recognize the MAC address, will basically filter the frame and don't pass the packet to the upper layer. All right. So one of the questions is the following. So let's say we are all connected to the same network. So it means that whenever I'm sending a packet, either is a unicast or broadcast frame, everybody should listen, can see the frame. So what is the purpose here of using, instead of the broadcast, using a unicast one? It means that instead of filtering at the layer 2, if I'm using the broadcast, I need to go up to layer 3, check what is the IP address of the packet, and based on the IP packet, in that case, I will be able to know if the packet has the destination. So Ethernet will bring a benefit here. And the benefit of this is you should always remember that the layer 3 on your computer runs as a software. So it's in your operating system. The layer 2 is hardware. So which means that if I need to filter a packet at layer 3, I need memory and CPU. Okay? But if I do the filtering on the hardware, I'm just going to use power. So we're using the MAC addresses just to be able to filter as early as possible the traffic that is not intended to us. So it means that if I need to send you a frame, I can use a broadcast, but everybody's going to be bothered because you will need to check the IP packet to make sure that you are not the destination. If I'm using the MAC address of the destination, then everybody else will be able to filter the frame without referring to IP in order to discard any packet that we are not the destination for. Do you understand the benefit of using Ethernet on top of IP? So it brings just as a benefit of filtering much earlier the traffic instead of only using IP. So that's the reason here, whenever we know the IP destination, we should find a way to tell what is the MAC address of that destination. Because any host have an interface, and that interface comes with the MAC address. I think that we already explained, maybe not yet, but the MAC address is given by the manufacturer, okay, which is not the case of the IP. So now what is happening? So let's say you need to communicate with another host. And let's say this is a destination. So that destination have an IP address plus a MAC address, okay? The MAC address, you buy your computer with a MAC address because it's already hard-coded on your interface. The IP, we'll see how we learn it. So it means that now when I want to send a packet, I can do two things. Either I can broadcast, but we said that if I broadcast, everybody going to receive the traffic, sure, and we'll need to ask IP to filter the packet. If I put the MAC address of the destination, that one here, it means that everybody will still receive the frame, but will be able to discard it pretty early. And that's really good, being able to do this. Now we have another case because we're not always connected to the same network. We may be on another network. So here I have network A, well, then let me put maybe in the opposite. So I have network 2 and 1. So it means that now I need to send a packet, but I need to go through a router. And as you may remember, when I send a packet, the packet need always to identify the source and the final destination. But in the middle, I need to indicate that this packet need to go through a router first. So one first hop, and then another hop to reach the destination. So how can I tell to the network that actually the packet need to go through the router? If I change the IP header, I lose the IP of the destination. And so then I cannot forward the packet beyond the router. So the trick here is to do what? Is to keep here the final destination, which is D. And in the MAC address, whose MAC address am I going to use in order for the packet to go first to the router? The one of the router. So that's the trick. So Ethernet going to help me into passing the packet through each intermediate hops before I get to the final destination. And that is how it works. So now we have two questions we need to answer. First, how can I know my IP address? All right, so that's not obvious. Knowing my MAC address is pretty simple because it's available on my hardware, right? How can I tell what is the MAC address of the router? How can I tell what is the IP of the destination? Because once again, when I send the packet, I need those to fill those information in the header of the frame and in the header of the IP packet. So we need to answer those questions. Okay? So basically, okay, so this is it. So when we forward the packet on the same network, so if we are connected to the same network, the header IP is the source and the destination. The MAC addresses are the source and the destination. If I'm not connected through the same network, I need to specify in IP still the source and the destination. I cannot identify anything else than the endpoints. And now, thanks to the frame, I'm going to have the MAC address of the previous hop or the source, depending on where I am, and the one of the next hop. You remember we had this question when we did the overlay question. So in order to be able to communicate, what should I know about myself? Okay, what should I know about myself? The thing that I should know is my IP address. First thing. I need to know the subnet mask of my network. And we will see that this is important because this is the only way I can check if the destination is on the same network. We need to share the same prefix. So to know if we share the same prefix, I should know what is the mask of my network. So I need to know my IP address, my subnet mask, which is obvious, the IP of the gateway, who is the router which actually will allow you to exit some traffic outside my network, the local DNS, because usually I need to learn what is the IP address of the destination, and most users, they will provide me with the name of the destination. So if I don't know the IP, I should be able to send a query to DNS, and I do this through the local DNS server. How can I know this IP? I still need to know the IP of the local DNS server. I need to know my MAC address, so that is easy. That is available on my interface card, right? The constructor provided with the card when I buy it. And those things, all those parameters, okay, except the MAC address, so everything else, we will see that either you need to configure manually, or we can use a protocol which is DHCP. So DHCP is a protocol will allow you to discuss with a specific server, which is called a DHCP server, and that server is in charge of sending you all those parameters here. So either you call the admin and he tells you, okay, so you need to set up that DNS, that mask, that IP, and so on, or you do it automatically, dynamically on demand. Regarding now, the DNS, right? The destination. So I need to know the IP address of the destination. Easy. We already said DNS will let me learn what is the IP of the destination. I need to know the MAC address of the destination, whether it is the final destination or the next hop. So that will be provided by another protocol that we call ARP, right? So we have DNS, ARP, and DHCP. Regarding the IP, we need to know the IP of the destination or the gateway, all right? And so as you may see, we have three protocols that we need to study on top of DNS, ARP, and DHCP, which actually will help us learning about all those parameters that we need, all right? So those two protocols, so DHCP, ARP, and obviously DNS, they help you doing a mapping. So DHCP do the mapping, giving your who you are, you're going to learn your IP. For ARP is giving the IP of a destination, you're going to learn the MAC address of that destination. And DNS giving the name of the destination, you will learn the IP of the destination. Okay? So you see, those protocols are super important. And there's something common about all those protocols, meaning DHCP and ARP. They use broadcast, and we will understand why broadcast is so important to those protocols. So let's start with DHCP if you don't have any questions. So let's see. So as we said, so when it comes to configure your the parameters of your IP TCP stack, you need some information. So either you can do it manually, and you can do it on any operating system. So here I have the example of Windows, Mac OS, and Linux. You may go to your network parameters, configuration, and they will ask you IP address, mask, gateway, DNS. IP, mask, gateway, and DNS. The same goes here. IP, mask, gateway, DNS. And if you don't have those, you cannot communicate. That's the way it is. So hopefully, we don't need to do it because nowadays we don't do manual. Most of the time, we use DHCP. And DHCP is a protocol which require on your local network to have a specific server, which is a DHCP server. Okay? And at home, who is the DHCP server on your network? But this is your internet box. So your internet box is doing DHCP, gateway, local DNS, Wi-Fi, what else? firewall, probably, NAT. So you see, so it does a bunch of stuff, okay? And Ethernet if you are putting cables, absolutely, Thomas. So the DHCP, and this is really important because the DHCP is not only about the IP address, it's about all those information. So it will give you an IP address, which you need to update pretty often. Why? Because it's always giving for a limited time. So this is like a soft state. So when you get that IP, you need to renew the IP. So the lease time could be a couple of hours, could be 1 day, but it cannot be infinite time. So you need to renew pretty often those information. The mask, okay? The local DNS, the IP address of the local DNS, and the IP of the gateway. That's it, okay? So the question now is, okay, but still, in order to receive all those parameters that I need to contact a DHCP server. How can I know the ID or the IP of the local DNS server, DHCP server? Okay, how do I know the IP address of the DHCP? All right, so hopefully we will see that since we cannot know, we use broadcast. And broadcast is like you shout out a request on the network and you say, who is the DHCP out there? So you contact everybody on the network because one of them should be the DHCP. So you see, so whenever you need an IP, everybody will hear about it on your network because you use the broadcast. Then we need ARP. Why? Because you see that here, the only information you have, it's the IP of the gateway. But do we need the IP of the gateway? No, because in the packet, you put the IP of the destination. So usually, what do you need to know about the gateway? Is it the IP or the MAC address? The MAC address. So hopefully, now that you have the IP, thanks to ARP, you're going to learn the MAC address of the gateway. And that's what you use inside the header of your frame, okay? And DNS, of course, because this is what's going to help you tell what is the IP of the final destination. All right. So as I said, so in all those protocols, so either it's ARP or DHCP, we use heavily the broadcast. Why? Because I don't know the IP address of the server. I don't know the DHCP, the IP or the MAC address of the server. So if I don't know, I should send the request to everybody. So I'm doing broadcast, okay? So in the case of DHCP, the server will receive your request, and he's the only one who will answer. And regarding ARP, when I send the request, is whoever I try to learn the MAC address will answer, okay? So in two cases. So because broadcast is super expensive, and I may need to contact the server pretty often, what I'm doing, I'm using caching. So when I said that we have a lease time, the lease time means that, okay, I'm giving you those parameters, like your IP address, and you may use it for the next hour. In 1 hour by now, you need to renew the lease. You need to renew your IP address. So instead of broadcasting all the time, I'm using caching, such as those information gonna be flushed, but in 1 hour. So this way, I don't have to pay the price of broadcasting so often. So those are kind of soft states, as we already explained them. Soft states, those are just states that don't need to be cleaned explicitly. What I know is once I install those states somewhere in my memory, they will be flushed automatically after 1 hour, let's say. Okay, so it's pretty easy to maintain those states. I don't need to worry, oh, why should I remove them? No, okay? They're gonna be flushed automatically. Okay, so let's discuss about the DHCP. So the DHCP, once again, is a protocol where actually you have a server, and the server, the objective of the server is to let you learn. It's gonna give you the parameters that you should use. IP address, subnet, which is the network address of your network, whatever, the DNS, and the IP of the gateway. That's what I need. And that's why I have the DHCP. Okay? So the DHCP is basically using 4 messages. There's the discover, the offer, the request, and the acknowledgement. 4 messages. Let's see how it works. So here I have a first client. He sent the first message, which is the discovery. So big question. So do I have an IP address yet? As a client, do I have an IP address? If I'm contacting the DHCP, it's probably because I don't have any. All right. So, but still, I'm sending an IP packet. I'm sending an IP packet. I need to put some information inside there. I cannot put void. I need to fill the information regarding the source IP address. Which IP address am I going to use? Any idea? Those are very good answers. We use the all zeros. This is a very special IP address that they will allow me to use during that very short period where I have no other choice than using that one. Okay, so this is the unspecified IP address. And as a destination, do I know the IP of this guy? No, I'm just arriving on the network and the IP could be anything. So what am I going to use? I'm going to use a broadcast, but at the IP level. And the broadcast is 255, 255, 255, oh my God, 255. Okay. So now I'm receiving the answer, which is an offer. And inside the offer, once again, I have the IP address I can use, the mask, the IP of the gateway, and the DNS, plus a lease time. Okay, you cannot use it for more than an hour, whatever. Okay, so now giving that request, so can you give me again what is the source and the destination of this message? It is still broadcast. And I will explain you in a minute why it's a broadcast. But yeah, that doesn't make any sense, right, guys? I mean, I know the IP of this guy. What should I do? A broadcast? Oh, there's a reason. I'm sorry about this. And basically, yeah, the same goes here. When I answer, can I answer to the IP address all zeros? Can I answer to all zeros? Is no one. So what about this message? What is the destination of this message? Yeah, broadcast again. So how many broadcasts until now? 1, 2, 3. 1, 2, 3. Wow, that's pretty expensive, right? So everybody is affected by this traffic. Yep. Yeah, well, that's the way it is. All right, so let me explain why this one here, because this one is very tricky, right? I mean, because you see, guys, the DHCP server is a super critical server on your network. If there's no DHCP, you cannot communicate anymore. So instead of having one, I have multiple ones. So it means that when I receive this first message, how many replies? As many as servers. So now I'm receiving multiple offers, but I'm not going to use all the offers. Only one is interesting, is relevant for me, right? So now what I need to do when I send a request, okay, when I send a request, I need to do what? I need to answer to one of them while declining all the other offers and say, you know something, there's only one winner here. All the others, they lose. So either you send as many requests as offers you received, or you may kill multiple birds with one stone. And by sending a broadcast, that's what, man, why I don't want to put the second one, okay? By doing a broadcast here, this is what I'm doing. I'm answering one message that everybody gonna receive, including all the servers. So I don't need to answer to each of them to say that, okay, no, I'm just sending this. So this one is a broadcast because I don't know the IP. This one is a broadcast because I'm using the 000, and I'm still using the 00 here because I cannot use, I have multiple offers. I need to use one. And so now I'm going to answer, and yet again, I haven't yet finalized the transaction regarding which IP should be used. So here, this is when I'm going to confirm, okay, you may use that IP since you accepted mine, and you may start using the IP. When we have the server, so once again, the offer message, okay, actually we are receiving multiple offers. Okay, so that's the reason in the 4 messages, and I'm not sure, do I have, no, I don't, oh no, it's here. So that's the reason here, what we have now, if I put the IP addresses, you see that here, unspecified and broadcast. This guy is answering to everybody on the network because of the all zeros here. All zeros, I need to do this. And then I'm answering the broadcast. Why? Because I have multiple servers here, and I may receive multiple offers. So that's the reason. And then the last message is also broadcasted because I haven't yet the IP. So once again, I'm using like an ID here, which is like a random number that I should be the only one using. So when the server is answering to one discover, he's using the same ID. So you may be able this way to match a discover with the corresponding offer. Since there's no other information here that will let you know who is the client, you have a transaction ID, which is supposed to be unique because it's random and won't mix and mess with everything else. That's a very good question. Okay. All right, guys. So this is how the DHCP is working. Regarding the question from Lei, so what is happening at your home, right? It's a little tricky because let's say this is your computer here. In the middle, you have your box, right? And here you have your ISP, okay? So the ISP will give you by DHCP your public IP address, okay? And so obviously, yes, the DHCP, here we have multiple DHCP on the ISP side. So locally, this one is also a DHCP locally for you. And he's giving you, what we'll see later, a private IP address. Okay? So hopefully, if the box is down, you may reboot your box. So you don't need to have multiple DHCPs. So the multiple DHCPs are on the ISP side because he gives you the public IP. And on this side, you have another DHCP server, which actually gives you the private IP address. And here you only have one. Okay, so I'm sorry, but only one. And if it doesn't work, as usual, we reboot the box because something is wrong, okay? So basically, I'm the client, this is a server, and this guy also is a DHCP server for this client here. So you see, so you have multiple DHCPs, one with your ISP and one with the local host, okay? Makes sense. So this guy, your box is a server and a client at the same time. All right. Okay, so we're done with this. So basically, just to tell you that there are multiple ways of allocating the IP address. So either the IP address is like selected randomly by the server. So he have a pool of IP addresses and he's using the next one. Most of the time, what's going to happen, you keep a state and you may, if you check the traffic that your computer is sending, usually when you keep in memory the IP address that you were using in the past. So whenever you are back on the network, you're going to try to ask for the same IP again. So usually the IP doesn't change that often because it's just like renewing the lease that you already have, even if you reboot your computer. So that's crazy. And so that's the reason for the lab, you need to use MyTrace because otherwise, if you try it on your network, you won't be able to see the random stuff because there's a memory. In some companies, what they do, they need to know your MAC address. So such as depending on your MAC address, which is unique, you're always going to receive the same IP address over and over and over. They do that to be able to track you because you see, if the IP address is allocated randomly, depending on the time of the day, it's really hard to know who was downloading some BitTorrent file, right? But now, if the IP is always allocated to the same user, because of the MAC address, it's pretty easy to track the user. So in some companies, you may also ask the DHCP to give an IP address based on the MAC address of the request, all right? Again, it could be random, all right? Regarding the lease time, there's a trade-off here. So there's not any perfect value, but it makes sense that if you have a very little number of IP address and you need to share those IP address with a lot of hosts, the lease time should be super short. So it means that you're going to reallocate the IP address often, such as everybody can have a little bit of the IP address over time. Okay, so you may have a small one if you have little IP addresses. If you have a lot of them, doesn't matter, you can give a big lease time, right? Another thing about the lease time is super important. Why? Because this way, we don't need to rely on the client to release explicitly the IP address to say that, okay, I'm done with the IP address, you can take it back and allocate it to somebody else. By having the lease time, whatever happened, even if somebody's crashing and cannot release properly the IP address gracefully, right? In that case, doesn't matter. The server say, okay, I give him a lease time. The lease time is up. I'm going to reallocate the IP address without informing the client. Right? So it's also very, very handy to have the lease time. All right. So if you don't have any questions regarding DHCP, we may move to ARP. Any questions regarding DHCP? Is it okay? So what I didn't say actually, and this is quite important actually, is the fact that DHCP is running on top of UDP. So can anybody explain me why DHCP should be on top of UDP? I need a connection, and when I have my TCP at the client and TCP at the server, right? If I need to send the SYN, can I use the 0000 and the broadcast to do the SYN? No, I cannot, obviously. So since TCP is not an option, I'm using UDP, not because it's better, it's just because I have no choice. And in UDP, there's no stage, there's no connection. So it's fine. I don't need to keep any ID regarding the client and the server. So that's the reason I'm using the transaction ID, all right? So you may check the port numbers that are used by the client and the server. So DHCP have specific port numbers that I may use, right, on both sides, such as everybody can hear the request, but it's only if the server is listening on a specific port number that actually he will answer, all right? Okay. Okay, guys, so let's move to ARP. So what about ARP? So we already explained that basically whenever you send a packet, the packet will be encapsulated in a frame. And yes, I need to provide the IP of the destination for the packet, but I need also to provide the MAC address of the destination. That's the way it works, right? So what it means that for each destination, local destination, I need to know what is the MAC address. So I will first need a table, which is kind of a cache, where I'm going to list for each IP addresses the corresponding MAC address that I learned. So either of those entries can be manually configured, so I can create them statically, or I can learn. And to learn them, I may use a request. And the request is basically a message that I'm going to broadcast on the network. All right? So basically, I'm going to ask everybody who has this IP address. The answer will be, here is the MAC address corresponding to this IP address. Okay. Then when I receive the request, what I'm going to do, I'm going to create a new entry in the table with a TTL, because the IP address may change. I want to keep the table as small as possible. So for all those reasons, the entries will expire pretty often, and I will need to send a request in the future again. Okay, so it prevents for a short period of time, but I will need still to broadcast. So why I'm saying this is because sometimes people may tell you that, oh, we have the table because we don't do broadcast. No. We still need broadcast, but we don't need it so often. All right, but still broadcast is very important. So let's look how it works. So once again, I have the table. So before I send the IP packet, I'm going to check if I have the MAC address inside the table. And if it's the case, I'm going to encapsulate the packet inside the frame. Fine. To add a new entry in the table, I may do it statically, as we said, or I may broadcast a request, receive the reply, create the entry in the table, and then send my packet. And as I said, any entry is created with a TTL because they need to be refreshed. So if I look at IRP, actually IRP is a protocol running on top of Ethernet. So it means that when I have my layer 2 here, which is Ethernet, on top of this, I have IP, but I also have IRP. And if I look inside the frame, the type that I have here which is 0800 for IP and 0806 for ARP, will tell me what is exactly encapsulated here. So basically, if this is a request, what is the destination that I should have here, please, guys? If it's a request, what is the destination MAC address that I have? Yes, it's a broadcast. That makes sense, right? Because I don't know the MAC address of the destination. So if I don't know the MAC address of the destination, I need to broadcast, right? So this is when it's a request. So how can I know if the message is a broadcast or not? Well, I need to check inside the message. So in the message, what do I have? I have multiple fields, as usual. And what I have first, you need to understand that ARP was designed not only for IP and Ethernet. It was a protocol, what is supposed to be a generic one. So that's the reason I need first to explain what is the type of the layer 2, what is the type of the layer 3. So we have special values. So for instance, if it's Ethernet, this is type 1, MAC addresses. If it's IP, here, did I give it somewhere? I will put 0800 even here to explain that this is IP. All right. So then I need to provide the length of the MAC addresses, the length of the IP addresses, 48 and 32, makes sense. Then for the operation, I will say if it's a request, it should be 1. If it's a reply, it's going to be value 2. And then, obviously, the MAC address of the source of this message, the IP address of the source, the IP address of the MAC address of the destination of this message, and the destination MAC address of this message. So let's look if you have been following. So let's say, I'm going to put in red. So let's say this is 1. This is 0800. This is then, what is the value for the HLAN in that case? The size is 48 for Ethernet. For IP, what is the length of an IP address in bits? Okay. This is a request. So if it's a request, we said that this is FFF. Then, can anybody tell me what is the destination here? What is the value here? Let's say I have A and B, and I send a request. I have MAC B, IP B, I have MAC A, and MAC IP A. So if it's a request, what do I have here? Okay. What is the IP here that I have? IP of A. What is the MAC that I have here? Destination. Okay. And sorry. And here the IP of who? Yeah, but in that case, if I know all of this information, what do I need a request in that case? Right? If I already know the MAC address of B, why should I send a request in that case, guys? Yes, so here, no, it's not the broadcast. Since I don't know it, what should I put here? All zeros. And I need to put, we said how many? 48 zeros, right? Because the MAC address is 48 bits. So I'm going to put all zeros. Okay, guys? All right. Another thing that you should be careful is the fact that, but this is a mess that they did in IPv4. When I send now the reply, okay, the reply is once again hardware type 1, 48, 0832, 2, and the source, if we have B and A, the source now is B, so I have the MAC of B, I have the IP of B, I have the MAC of A, and the IP of A. So you see, you reverse the two of them, you swap them because now the source is the source of the reply, which is a little awkward, all right? Understood? So they swap the two values. Understood? Well, I don't think that makes sense, and they're changing later. So, but ARP is still very awkward. One question, so when I send my request, okay, you may see that when I send a request, so I send all the information regarding A, MAC A and IP A. Why do I need this? B will need to reply, and to send the reply, I need those two information to be able to reply to A. So that makes sense, correct? And this is what I'm going to put inside the table of B. I'm going to enter those information in the table. So guys, let's say I'm on a network and this is A. And A wants to know the MAC address of B. And I know the IP of B. But too bad because there's no B on my network. So I'm going to send a request. What's going to happen? So what it means that ARP will send only one request, okay? And if there's no reply, we do nothing. So what's going to happen? Let's say if it's TCP, we lose a segment because the segment won't make it out, don't receive an acknowledgement, so you will try to resend the segment, do ARP again. And that's the way it works. So yeah, so ARP is not reliable. One shot, doesn't work, no problem, okay? So yeah, so ARP is not reliable. Let's take an example maybe. So here, what do I have? I have two networks, as you may see. So you have A and B, and they sit on different networks. Okay, so here, let's say I know the IP of B, which is 222. So first thing that I need to do is to check if B is on the same network with me. How can I do to tell if B is sitting on the same network? How do we do usually this, right? How can A tell that, oh, B is not sitting on the same network? So I don't know, the mask here we can say is a /24. So I'm going to check the two prefixes. We're not on the same network. And hopefully, I know the IP of the router because this is my gateway. So it means that all my IP packets that need to go outside my network will need to go through the router. So which MAC address should I learn? I'm going to send a request asking for the MAC address of the router. Yes. So do I know the IP of the router? Yes, I know it thanks to DHCP, right? DHCP gave me the IP address of the router. So I need to send the packet to the router, so I need to find the MAC address. So then the router going to answer. And basically the packet that I'm going to send will be a packet with the IP address of B, 2222, but the destination at the MAC layer, so this is the IP destination, the MAC at the destination will be the one which is E6 for B, which is a router. So this one is B. So then the packet, the frame is received by the router. The router will check the header of IP, check that, oh, this is not my IP, so I need to forward the packet because I'm a router. So he's going to check his interface. He's going to compare it to B. And he's going to say that, oh, but B is sitting on the same network as this interface. So I need to send an ARP request to B. So, but still, it's a broadcast. And B will answer, right? And B will answer with his IP address. So if I look at the packet here, so if I look at the IP destination, we still have B. No, B 2. Okay, I have 2, 2, 2, 2, 22. And regarding the MAC destination, I have B. And the MAC destination is 49 to 8. Okay, so you see, so multiple steps, 2 broadcasts. One on the first network, a second broadcast on the second network, right? Hopefully the tables may help here because the information may already be available in the ARP table, okay? But any host need the ARP table, all right? So this is how it works. Okay, you may run okay, so let's talk about the middle boxes here, all right? And the middle boxes, an example is NAT. Any other questions regarding IRP, or should I move forward with the boxes, with the middle boxes? Is that okay? So let's go with the middle boxes. So I'm sorry, I'm trying to open up here to multiple things. But basically, and that is a follow-up on what is Adrien saying, is basically nowadays in the internet we have a lot of requirements, right? So what do I mean? Yes, so the IP addresses of the host change a lot, right? My computer is connected to the library, then in the classroom, then in my office, then in the canteen. So you see computers move a lot. They need to change the IPs quite often. We don't have enough IP addresses. We already said that the IPv4 addresses, we don't have enough. And even if I want to configure all the hosts at NYU with a public IP address, I probably don't have enough of them. Then I have some security issues. I mean, how can I control the traffic from my users? How can I prevent them from using a local server, right? Let's say I'm a student, I want to set up a server and share some content. I'm not supposed to run my server on the local network of NYU. I don't have the authorization for this. So how can I prevent anyone from acting as a server within the campus, right? So there are some security issues. And then there are some performance concerns. I mean, how can I make sure that most of the bandwidth is not used because I'm doing Netflix, right? And I want to make sure that all the bandwidth is used for Zoom without anybody watching Netflix during lunch will prevent other students from attending Zoom, right? So how can I make sure that the bandwidth is allocated in a fair way, right? And allow for some priority traffic, right? And so on. So because of also those concerns, so that's the reason we've seen that actually the internet have been designed, right, with in mind the end-to-end principle. But what we're doing a lot now is like we're adding new functionalities in the middle of the network, but without changing the IP layer. So it means that instead of starting, changing the way IP is behaving, which is a nightmare because I need to standardize, to update all the internet to make it compliant, right? What I'm doing here, I'm going to add few functions in the network in some specific locations. And in order to put those functions at those locations, I'm going to introduce those boxes, right? So I put them in the middle, somewhere between clients and end hosts, okay? Without even the knowledge of anybody in the middle, okay? And basically, there will be messing up with the traffic without you even knowing. So for instance, is a cache the same? Yes, it is. Because for instance, when you download a web page, do you know if actually it comes from the server or from a cache? You don't know, right? The firewalls go the same. I mean, how can you know why you couldn't connect from outside, right? Is it because there's a firewall or the great wall that won't allow you for the traffic, or is the server down? You don't know. Traffic shapers, the same goes here. So what I'm going to do, I'm going to slow down some traffics, okay, which use too much bandwidth, right? Such as I can leave some space for others. We have also IDS. So this is also something that the companies are using a lot. So they monitor the traffic such to prevent any attacks from outside. So this is an intrusion detection systems. So you need to keep recording the traffic that enters your network to be able to say, oh, this one looks suspicious. Somebody's trying something weird from outside. And we have the caches, all right? So we already discussed about the caches. So there are many examples of this, and that's a huge business, right? Okay, so a lot of companies will basically sell those boxes depending on your requirements, right? And even, I mean, it's not only companies, but even countries, right? I mean, anyway, not going to get into the details, but so here, the function that we are looking at is the NAT, okay? Translation. And it's been designed waiting for IPv6. So at the beginning, IPv6 was in the phase of being standardized in the 90s, and yet we were running out of IPv4. There were no time to wait for IPv6. So people say that, oh, in the meantime, right, let's try to find a way to still be able to connect as many hosts as we can, even though we don't have enough IPv4 IP addresses. And what was the idea? The idea was pretty simple, but very dirty in the way they did the design. And even though it's dirty, we're still using it today, nowadays. So what do we do? So I'm sorry, it's very small, but the main idea is to say that NAT is for medium-sized organization who don't have the money or cannot afford to buy too many public IP addresses, okay? The same goes with us, right? If you want to have as many IP addresses from your ISP at home, they're going to charge you a lot of money, right? So usually, whatever is the number of hosts that you have at home, you can connect your iPhone, your iPad, everything, and even though you only have one public IP address, and that public IP address is used by your box. So what about the other computers? Well, what we do, so once again, you have your box. So the box is receiving from the ISP a public IP address. And within your local network, you only use private IP addresses. So what do we mean by private IP addresses? It means that they are usable, they cannot be used outside of the network. Okay? So you have one public, you have many private IP addresses. And so what you're going to do, you're going to hide behind the public IP address, which means that whenever you need to send a packet outside, you send it using your private IP address, but the NAT is going to replace the private IP address with the public IP address, such as from outside, everybody sees the network, such as one single IP address. So when you receive the reply, you replace the public IP address with the private IP address, and that's it. So that's the trick. So basically, you hide everybody behind the public IP address. Everybody's using a private IP address, which is not visible from outside, giving that the header, okay, will be modified by the NAT. That's the way it works, okay? It looks simple, but it means that any outbound traffic will have the private replaced by the public. Any inbound packet will have the public replaced by a private IP address. So let's look at how it works. So let's say here, obviously, this is my private network. So as you may see, I'm using the 10/8. This is by convention one of the private IP address that I can use. And most probably for those who are in the dorms or in the campus, probably I think on the campus you are using such IP address, right? There are a couple of private IP addresses by convention, right? It's just because we know that those are private. Okay? Yeah, can make sense. And so here is the public IP address, the single public IP address, which been allocated by your ISP. That's it. So now let's say somebody needs to send a packet. Okay, so I'm sending a packet. So this is the destination IP address with the port number. So what you're going to do, you're going to swap, you're going to remove and rewrite the private IP address with the public IP address. So you see the source have been replaced by the public IP address. So this one replaced by the public. So basically you send it, okay? And so then you replace, when you receive the inbound packet, you remove the public IP address, and instead of it, you put the private IP address. Okay? Understood how it works? So you need some state here, where you need to remember that, oh, this guy sent this packet to that destination, so I need to replace it for the inbound packets. Understood? Is it okay? So you see, so it means that if at some point, all right, so let's say if at some point I'm receiving a packet and the table is empty, no entry here, what's going to happen for this inbound packet if there's no entry? I'm going to discard the packet, yeah. I'm going to drop it, or I'm going to try to make sense. Maybe I'm the destination. But if I was not expecting any packet, I'm probably going to discard it. All right, so move it. Now I have a second question. So you see I have my table here. So maybe I should, let's create it this way, okay? And at the same time, I have a second user who wants to communicate here. So can anybody help me with creating the new entry that I have? What is the second entry? So I have a first entry because of this packet, so packet 1 here. What about the packet 2? What is the new entry that I'm going to create because of that second one? So it's 138.76.29.7. And what is the IP of the private 10.0.0.3? Thank you, Lei. So 3. All right. So I have those two entries. But now let's say I'm receiving the two packets. How can I know which one actually was for this one? You see that now I'm confused because I have the same public IP address with two private IP addresses. So how can I match? You see, so now we have a trouble. So in order to allow multiple hosts on the local network to be able to communicate, I'm not going to change only the IP address. I'm going to as well rewrite the port number. So what I'm going to do now, when I'm sending this one like this, oh, this is the example, all right? So anyway, so you may see that here we have the trouble anyway. So I don't know how to change it. But what I'm going to do now is instead of just giving this one, in order to allow for two ones to be able, I'm going to use the port number as well. And the port number will be rewritten. So now if I have a second one who actually goes outside, and I create a new entry for that new one, you see that that new one will have a new port number. So now in the table, what will help me ID that was that host on my network will be the port number, because the public IP address is not enough. So the port number, you remember that on the client side, how do I choose the port number? Do you remember how we use the port numbers? Randomly. So does it have any, is the value relevant, or can I use any value that I want? Yes, any value. So the NAT people say, okay, if it doesn't have any meaning, I'm going to give a meaning to the port number. And that's what I'm doing here. So I'm using the port numbers, such as those port numbers are unique for each of the hosts that are communicating. Such as when I receive back the packets, I'm looking at the port number and I know exactly who was the source. So first of all, do I have a limit on the number of hosts that can communicate? Do I have a limit? Yes, I have a limit, because I only have 2 power 16 values possible. So exceeding that number, I'm blocked. And as we said, in a network, it should be scalable. You shouldn't say that it works for that limit. That's bad design. A network design is no limit. Okay? The other thing that we have, and guys, again, that's the kind of question you should ask, is once I create an entry, how long should I keep the entry? Is there a good answer? You see, you need to put a time limit. And it's really hard to have a good idea of the time limit here, because for one request, do I know how many messages am I going to receive and when am I going to receive them? No, I don't have that information. But I cannot keep that entry forever. Okay? So that's also a design, as I said, when you start adding a state somewhere, states are a nightmare, because once again, you can have a lot of them and you need to clean them at some point. So when? And if you cannot answer when, it means that the design is not good. So if it doesn't make any sense, it means that that state somehow is not. The other thing is, okay, so can you tell me when I send the message, what am I going to change in the headers? So can you remind me what are the fields that should be changed for the outbound packets? So the IP address of IP source. What else? The port source. Any other fields that I should change, guys? Or that's it? Yes, the checksums. IP and checksum TCP. You see, so it's getting super dirty here because somebody is messing with your packet, not only in the IP header, but also in TCP, and have an impact on the checksum, you know? So will you allow this? Somehow, as we said, the IP was designed, internet have been designed with end-to-end principle. The header shouldn't change. And even though somebody's changing this in the middle. So somehow something is wrong. Anyway, so because we're running out of time, so let's do. So we need to maintain the mapping table, okay? Once again, you need to create those kind of entries, as we already said, right? Private public IP address, port number, new port number. So this is the entry. We should be able to tell how long should we keep this binding in the table, for how long, and it's really hard to tell, all right? So removing those states, it's hard to tell when, okay? So there's a lot of objections. So once again, the port numbers are not supposed to ID a host, but that's what we're using them for. You know, we overload the meaning of a port number to let them ID a host. That's not supposed to be the right thing to do. They say that the NAT is supposed to block TCP. So some people say that, but it's good that we're using a NAT because if a student, for instance, want to have a server running, if he have a NAT and he have a private IP address, nobody will be able to set up a hidden server here, okay, behind the NAT. I know, but if in your NAT you have states and I can discover what are those states, can I still send some packet within the NAT if I can tell what are the states that are currently in the table? Yeah. So even if it's supposed to protect your network, if as an attacker, I can tell that, oh, somebody have a translation here that is long time enough in the table, I may send some fake packets that I can forge, such as I can attack one of the computers. And since I have no clue about what is a good value of the TTL, I may use it from outside to send some forged packets. So it's not that safe, actually. Once again, the end-to-end principle tells us that nobody should change the IP header, but though here somebody is written the IP header. And so I'm putting states, and whenever I have states, it's a nightmare because it can become no scalable. So the thing is, you may remember, and I want to conclude on this, even though I know I'm super late already. So the NAT, as you may see, will change the header of IP, right? Such as now you have on the public internet a new packet. Maybe a better design, we already talked about it, is to use a tunnel. Because the tunnel, instead of changing the header, you may add a new header on top of it as we keep the integrity of the packet. But in order to do this, I need to have an entry and an exit of the tunnel. So here you may see that, yeah, but how can I learn about the other end of the tunnel? Yes, that's a little more complicated, but that would be the good design here, right? So maybe I should have something that will let me create a new header by creating a tunnel in a clean way, by resolving. So if I know D, maybe I can have a system which actually give me the ID of the router. You see what I mean? Well, that's not the choice that they did. But anyway, instead of translating, I may do a tunnel, right? That would have been the good design. Or let's use IPv6. Nowadays, IPv6 is available, but we're still using NAT because there's no IPv6. Anyway, we're going to discuss about IPv6 later. So where is NAT? On your home router, we already said it. In some corporate or even universities campuses, that's the reason Thomas, who is on the campus, have a 10 dot something, right? But anyway, so even if nowadays NAT is pretty popular, the solution is IPv6, right? So do we need NAT with IPv6? No, everybody can have an IPv6 address. So no more need for private IP addresses. So anyway, that's the way it is. So we discussed together today about some important functions. So we completed DNS with the other ones, ARP and DHCP. All right, those are super useful because this is what's going to let you fill the header fields of your packets and frames regarding the source IP, source MAC address, destination IP, destination MAC address. Without those protocols, you cannot fill the information and you cannot send a packet. And we talked about the middle boxes, including the NAT, which actually is in the middle, must up the packets just because nowadays there's not enough IPv4 addresses for all the hosts on the internet. So we're using private IP addresses which need to be translated, which is not the best way because it goes against the design of the internet, which is end-to-end.